So hello everyone, welcome to OneClass. My name is Shanjida. I'm currently a second year human biology student at U of T. And so today I'll be going over some commonly asked chemistry questions, both at the high school / university and college levels. And if anyone needs any additional schoolwork help or needs tutoring, you can check the description box below. And other than that, let's get started. Okay, so our first question here says, what is the structure of cyclohexane? Okay, so cyclohexane is a cyclic alkane, so which means it's basically a hydrocarbon. It consists of cyclohexane. So this is basically a hydrocarbon, right? It consists of carbons and hydrogens, right? And so you can basically, since it says it's a cyclohexane, it means its structure is like a hexagon. Okay, and so and since it's a hexane, not an hexene or ine, it has single bonds. Okay, and so this is basically, you can say this is kind of like a ring. And so to draw this, so just draw this cyclohexane. Okay, oops. Okay, where like it's basically an hexane where you have 1, 2, 3, 4, 5, 6 carbons, and each of them, so like right here and here, here and here, these would be your hydrogens, right? And you have 12 hydrogens, and so your chemical formula is C6H12. Okay, so this is called a cyclohexane. And so basically it's kind of like a ring structure. Okay, and so that is why it's actually named a cyclohexane. Okay, and so you can also draw this in a chair conformation, and so where the conformation is considered as the most stable. Okay, and what I mean by this is that, so cyclohexane can be drawn as a chair conformation. And so this is basically your most stable form, stable structure or conformation. Okay, and so to draw that, we're gonna, so what we mean by a chair conformation, you basically have like this hexagon type of shape. Okay, okay, yeah. Okay, and so basically all your corners here, like all these points, are your carbons, and then you're just gonna draw your hydrogens. Okay, so we have axial and equatorial hydrogens, and so I'm gonna use different colors for those. Okay, and so I'm gonna draw all my axial hydrogens in green. Yeah, those are the ones that are going up or down. And so we're gonna have one more right here. This is also gonna go down, where this is gonna go up. And so now we're gonna draw our equatorial ones. Okay, and these are the ones that go sideways down, sideways up, and so and then you basically have this one going this way and this one going this way. Okay, and so this is basically your chair conformation for cyclohexane. Chair conformation. Okay, and so this is your formula, C6H12, and you can draw a chair conformation. This is how it looks like, where your axial hydrogens are bolded, right? These are your black ones, and so this is correct. So our second question here says, distinguish between the terms of electronegativity versus electron affinity, covalent bond versus ionic bond, and pure covalent bond versus a polar covalent bond. Characterize the types of bonds in terms of electronegativity difference energetically. Why do ionic and covalent bonds form? Okay, so there are a lot of questions here that we need to address. And so basically electronegativity is a chemical property. So I'll just write so your electronegativity is a chemical property. So this is basically stating where how well an atom is able to basically attract the electrons to itself, right? And so basically the more electronegative an atom is, like the more electrons it attracts to itself. Okay, so this is what basic electronegativity is. It's basically a chemical property, and where your electron affinity of an atom or molecule is defined as the amount of energy released when an electron is added to a neutral atom or basically a gas to or an atom to become negative, right? When you gain electrons, you become negative, the atom becomes negative. And so we can say electron affinity of an atom or molecule is defined by the amount of energy released when an electron is added. Right, so you can consider atoms when they accept electrons, right? When they gain electrons, they become negative. So they basically you can say forms a negative ion, right? Okay, so that's the difference between electronegativity and electron affinity. Now if we go to the key difference between an ionic and covalent bond. Okay, so let's first address what is ionic bond. Right, so an ionic bond is where electrons are shared. Ionic bonds is where you form. It's formed by a metal and non-metal, right? And so it basically donates, right, your non-metal. So I'll just say non-metal donates. Metal donates. Metal donates electron to non-metal. Right? This is in your simple terms. So you're not sharing, you're basically donating the electrons. And whereas, so an example of this could be, you can say NaCl, right? Sodium chloride. Whereas your covalent bonds, are formed by nonmetals, right? Between two nonmetals, basically. And so what they're doing in a covalent bond, they're sharing electrons. Okay, you're not donating electrons or accepting electrons, you're just basically sharing electrons between the bond. Okay, and so basically an example of this could be CH4. Okay, and so your atoms form a covalent bond in order to reach a more stable state, right? So basically, atoms form a covalent bond, to reach a more stable state. Okay, this is basically this is why covalent bonds are actually formed. Okay, and now if we go to if we go to pure covalent bond versus a polar covalent bond. Okay, so your pure covalent bonds are your pure covalent bonds are where the electrons are shared equally. Where electrons are shared equally among the atoms. Okay, and whereas in polar covalent bonds, right, this is where your electron negativity comes into play. So you can say so basically what you can say here is where your polar covalent bonds. Polar covalent bonds are ones where electrons are basically attracted more towards another, towards one atom. Okay, and so what I mean by that is, so what we can say here is that electrons are shared unequally. Okay, they're shared unequally, and where one atom exerts more more force of attraction. So it tends to attract more of the electrons to itself more. And so you know, as we mentioned with electronegativity, right? So electronegativity is part, so is a part, you can see it's part of a polar bond to distinguish a polar bond, right? So as we mentioned before, that electronegativity, when a atom is more electronegative, it tends to pull the electrons to itself more, right? And so basically this is what they're saying in polar bonds, is that you'll have one atom that's gonna tend to pull the electrons to itself more than the other. So, and this is, you distinguish a polar bond by calculating the difference. So you calculate the difference between the electronegativity. So you basically calculate the difference between the electronegativity of basically both the atoms. Okay, so you're comparing the electronegativity, and so the one that has the most that has a bigger electronegativity will tend to pull the electrons to itself, and also the difference between the electronegativity of both the atoms will basically determine how polar the bond will be. Okay, and so the key difference between an ionic is that donates an electron, right? And where you have shared electrons in a covalent bond. Ionic bonds formed between metal and non-metal, and covalent bonds formed between two non-metals, right? And so atoms form a covalent bond in order to reach a more stable state. And so when we're talking about pure covalent bonds, the electrons are shared equally, right? We don't have any polar bonds, we don't have electronegativity in this case. So, and when we're talking about polar covalent bonds, the word polar means that your electrons in the bond are not shared equally, so they're unequally shared. So that means that one atom is putting more force into attraction on the electrons than the other, right? And this is where your electronegativity comes into play, basically. So this is correct. our next question says, what are the Lewis formulas for the following ions? Okay, so what we have to do is, so what they're actually saying is to draw out the basically we have to first draw out the Lewis structures, or draw out the Lewis structures. And so to do that, in writing Lewis structures, we have to first find the total number of electrons needed to be distributed to count the first adding valence electrons, and then the formal charge, and the total number of electrons, and all of that. And so we also have to basically draw the bonding electron pairs, how many lone pairs are there, right? So this is what a Lewis structure is. And so basically the structure with the least number of formal charges, or have the smaller charge, is the most stable Lewis structure, right? And so the atoms, so let's say for A, we're doing A. This is iodine dibromide, Br2 plus. Okay, this is plus. Okay, so they have a total of 21 valence electrons. Okay, and to do that, so how I figured that out, we can say so basically 4 electrons are shared in 2 bonding pairs, right? So you have 2 bromides here and 1 iodine, and so you are gonna have, so if I want to draw this out, right, if I want to draw this out, you're gonna have I, Br, right? So you're basically having 4 electrons. So you have 4 electrons in this bond, and 4 electrons in the other bond. Oops. Okay, and so what we're gonna do here, right here, is that we have 4 electrons in 2 bonding pairs, basically. Bonding pairs. And while we have 16 are distributed as basically lone pairs, okay? So 16. Well, are not bonded, but are distributed as lone pairs, right? So if we look at our periodic table over here, right, and look at iodine, which is right here, right, it's part of the group 7, so it's gonna have 7 valence electrons, basically, right? So it's gonna form basically 1 bond, right? But since we have 2 here, so it's basically sharing 2, and so we're gonna have 2, 3, 4, 1, 2, right? So it's gonna have a full octet right here. Since it already bonded with its it has 2 bonds right here, it's gonna have a positive. And so if you look at bromine is also part of the group 7, and so it's gonna have 7 valence electrons as well. And so since you can see here that bromines are forming only 1 bonds, both the bromines, so it's gonna have 6 valence electrons, right? Because the other one, the 7th electron, is bonding with the iodine right here. Okay, and so we can basically say that so if we don't put the formal charge yet, and if we count the electrons, we're gonna have a total of 20 electrons, right? 16 plus 4, right? So we have 20 electrons in total. Right? And so basically, since we have 20, but we needed 21, right? Because we have 7 valence electrons from iodine and 7 from both the you have 7 from each of the bromides, so like you have 2 bromides, right? So you have 14 valence electrons, and so in total we have, in total we have 21 valence electrons. But you see here we only paired 20, right? And so we have 1 less of an electron, so this is why this is a positive charge. It has a formal charge of +1 at the central atom, basically. So that's basically on iodine. Okay. And so B says you have to find chlorine difluoride. Okay, and so to do this, so let's look at chlorine here. So chlorine over here, this is part of the group 7, and fluorine is also part of the group 7. So it basically, you can say the atoms of Cl F2 plus has 7 valence electrons from chlorine, right? 7. So since we have 2 fluorines in this case, right, we're gonna have double the amount of valence electrons, right? So we have 7 times 2, which is equal to 14 valence electrons from F2, basically, okay? And so you can say that in total, we have 21 valence electrons, right? 14 plus 7 is 21. But when we are gonna draw this out, right? So let's draw this out. We have Cl minus, or Cl, I won't put the charges yet. Cl, and I'll draw fluorine. Right, our fluorine here. And so your chlorine has basically 7 valence electrons, right? But you can see it's bonding with, so since it has 7, it only needs 1 more bond to fulfill its octet, but over here you can see it's forming 2 bonds, and so that means it already reached, so you can say here, right? So you have 2 electrons bonding with one of these fluorines, and the other 2 falling with the other fluorine. So you can basically say we are sharing 4 electrons here, right? And so, right, to reach a full octet, you need 8 electrons, and so you need 2 more lone pairs on chlorine. And so, and for fluorine, since it's only able to form one bond, right? Because it only has 7 valence electrons. So it is, both the fluorines are bonding with, are only bonding with one creating one bond with chlorine in each of the cases. And so fluorine, each of the fluorine will have 3 pairs, basically 3 pairs of lone pairs, 3 lone pairs basically, right? So you can see it's stable, right? Both the fluorines are stable. However, since chlorine over here is bonded with, has completed its octet basically, right? We can now count how many electrons we have bonded, or we have right here, right? So we have 4 electrons from 4 electrons that are from the bonds, from the 2 bonds, right? And we have basically 16, right, in 2 bonding pairs. Well, we have 16 electrons, right? 16 electrons as in groups. Or we can say, actually we can say here that we have 8 lone pairs. That means we have 16 electrons, right? And so you can see we have 16 plus 4 electrons. So we can say in total we have 20 electrons, right? In our structure, in our Lewis structure here. But recall we say in total we have 21 valence electrons, right? So since we're missing 1, right, which is because the chlorine over here bonded with 2 fluorine atoms, and so basically your central atom is chlorine and it would have a positive charge, a formal charge of +1. Okay? And now if you were to do C, which says, so this is cyanide, as carbon, CN negative, okay? And so, okay, so the same thing that goes for cyanide. So let's look at the valence electrons for each of the atoms here. So carbon, right, if you look at our periodic table here, has 4 valence electrons, right? It's in group 14 of 4. So carbon has 4 valence electrons. Nitrogen, right, you can look at nitrogen, has 5, right? It's in group 5, so 15, 5. It has 5 valence electrons. So in total we have 9 valence electrons, right, total. And so we can basically, so when we're drawing out, let's draw out the structure here, right? Let's draw it out. So see, so basically what we're going to have, since we have 9 valence electrons, we can basically, since one bond, you have 2 electron sharing, so we can basically say that we can form 3 bonds, so basically a triple bond between the 2 atoms, right? So we can basically say that okay, right? And so basically we have 3 bonding pairs, right? So we have 6, so we can say we have 6, so I'll just write it down here. So we have 6 electrons bonding in a triple bond. right? Okay, so since carbon can form 4 bonds, right? And can form 4 bonds basically, so you can also say here that carbon has 2 more pairs of electrons because carbon can form 4 bonds. And so nitrogen, on the other hand, has 5 valence electrons, and you can see it only paired with 3, and so it also has 1 more lone pair. Okay, and so you can see that, and now we have basically 2 lone pairs, right? And so this means we have 4 electrons. And so if you add the total number of electrons, right, we have 10. So if you remember that we only had 9 valence electrons, now we got 10, so we added 1 more electron, right? So when you're adding electrons, you're making it more negative, and so this compound would have a negative charge on carbon. Okay, so this indicates that there's an additional electron added into the bond basically. Okay, and this is why cyanide has a negative charge, while the other ones had a positive value basically. Okay, and so this is basically the answer. Okay, so we have here, this is what we have drawn, and the last one has a negative charge, and this. So the solution, correct. Okay, so our next question here says, how do you find the molar mass of argon? Okay, so argon, if you look at our periodic table here, argon is group 8, so it's a noble gas, so let's say argon, right? The symbol for it is Ar, and so this is a noble gas, group 18, which is also 8. If you don't include your transition metals. And so so from a periodic table you can see that it basically has 18 electrons, right? So has 18 electrons, and so it has a full outer shell, right? And so now we have to find the molar mass of argon. So we can basically say that to find molar mass, we can first relate this to the atomic mass. Of argon. Okay, so the atomic mass is, so to calculate atomic mass, of argon, right? So this is your number of protons plus the number of neutrons. And so if you look back at our periodic table here, it has 18 electrons, which indicates it also has 18 protons. Okay, and your number of neutrons is basically it's also basically it's basically the same as your protons, but in some cases it won't. And so we can basically say here that we can basically say that it's almost equal to 18 but not. And so right, we can basically say that it's we can also say it's 18, but since your atomic mass is given in your periodic table, right? For argon, it's stated here is 39. So we can also assume that your amount of neutrons is basically you get your number of neutrons from your atomic mass minus the number of protons. But let's say you didn't know the atomic mass and it was not given, so you would assume that the number of neutrons is 18, right? And you can say that this is 36, right? However, in most cases they will give you the number of neutrons or they will give you the atomic weight, and so we can basically say, right, since it's 39, we can say 39 minus 39.948 minus 948 minus 18, right? So you basically have around 22 neutrons basically, right? And so you get an atomic mass of around 40, right? Approximately 40. And so we can correlate this with, so basically you can say that therefore, so you can basically, the units is AMU, okay, 40 AMU, which means atomic mass unit. You can also, so you can say therefore the molar mass of argon is approximately 40.0 grams per mole. Okay, so when you're dealing with molar mass, your units are grams per mole, and so basically this is given in your periodic table. This is for one atom or 1 mole of argon, right? And so you can basically look this up in your periodic table and find it, but this was one of the ways you can relate molar mass with atomic mass. So this is correct. I rounded my number to 40, but this is the exact atomic mass or molar mass. So yeah, this is correct. Number 5, rank the following compounds according to their boiling point, lowest to highest. Calcium carbonate, methane, methanol, and dimethyl ether. Okay, so one way to classify or basically put in order the boiling points of the given compounds, we need to know the intermolecular forces, right? Because they play a big role in determining the boiling point and how much energy is needed to break that bond, basically, right? So stronger molecular bonding will be harder to break, right? Whereas, and would have a higher energy would need higher energy to dissociate the molecule. And so basically, when you have a higher energy, right, when you need higher energy, you need more heat, means you need a higher temperature and a higher boiling point, right, to change basically the solid state to a liquid or the liquid state to a gas. And so let's start with calcium carbonate, right? So let's say calcium carbonate, right? So calcium carbonate, as you if you recall that calcium is a metal, right? And so this is an ionic compound, right? And so so it has the ionic bonding, and ionic compound has strong intermolecular forces, right? So has strong intermolecular forces, right? And so basically it will have a really strong, it will have a high boiling point. And so basically, since this, if you look at the other compounds here, so calcium carbonate is the only one that is an ionic compound. And so basically ionic compounds have one of the strongest intermolecular forces, and so you can say that this is the strongest of them all, right? And so you can say this has the highest boiling point. Okay, and now let's compare this with, let's say methanol. Okay, CH4O. This can be written as CH3OH, right? Which is basically your methanol. All your alcohol is OH. So this form shows that there's a hydrogen bonding at the end of the molecular framework. So right, your OH is your hydrogen bonding. And so this means that the compound possesses, so that means that the hydrogen bonding is the strongest, right? It's one of the strongest intermolecular force. And so right, your hydrogen bonding is one of the strongest intermolecular forces. And so you can say that this is strong intermolecular forces. Okay, but to determine if this goes next, if this is one of the highest, let's look at the rest of the compounds in the list. Okay, and this is, right, this is a hydrogen bond, but this is not an ionic compound. This is covalent, or you can say valence sharing, right? So now let's look at the other one. So let's look at methane, for example. Okay. Or no, let's look at dimethyl ether. Let's going over right here. So like dimethyl ether, right? This is CH3. CH3, right? You have two methyl groups here. And so this is a polar molecule because you have your oxygen, your carbon-oxygen bond is more polar than your carbon-hydrogen bond, right? And so basically polar covalent bond, right? This is not an ionic compound, and so you can say it has dipole-dipole, forces, intermolecular forces. And so if you compare this with your hydrogen bond for methanol, dipole-dipole forces are relatively weak. So weak force, right? So you can say it has relative low boiling point. Okay, and so we have, so this is basically for dimethyl ether. We can now look at methane, right? So CH4. Okay, so CH4, we can basically say that this doesn't have any hydrogen bonding, right? So this is non-polar covalent bond. And so basically, since it's a non-polar because of its symmetrical structure, and so this has London dispersion. Forces, right? And if you recall, London dispersion forces are the lowest intermolecular forces, right, of your covalent bonds. So the weakest intermolecular forces. Or force, right? So this would have really low boiling point. So which means, you know, you can easily break the bonds, and basically change the state from a liquid to a gas, or a solid to a liquid and stuff. So it's basically easily break bonds. Doesn't need much energy, right? Much energy. So okay, now since we have done all the 4 compounds here, we can now start to put them in order from lowest to highest, right? So lowest to highest means you have the lowest you have the lowest boiling point, means it doesn't have much, so the forces between that molecule is very, very weak. And so since we have done it, we can say that methane, right, CH4, has the weakest bond, which is weakest intermolecular force, which is London dispersion forces. So we can say that methane is our lowest, right? So CH4. Okay. And so next we can say, so we can now have to compare dimethyl ether with ethanol, with methanol and calcium carbonate, right? So we can see that calcium carbonate has the highest, so this has the highest boiling point, so this would be our last. So let's compare that. Now let's compare, so we have dimethyl ether and methanol. So we can compare that methanol has hydrogen bondings, whereas your dimethyl ether has dipole-dipole forces, right? So dipole-dipole is relatively weak. It's weaker than hydrogen bonds. So you can say that this would have a relative low boiling point than methanol, okay? And so we can say that our next one is dimethyl ether, which is CH3 OCH3, right? And so this basically brings us that our methanol would be our second last one, so CH4, CH3OH basically. And so our highest, we write this, okay, CH3O, CH3OH, and so our highest would be calcium carbonate, right? And because calcium carbonate is an ionic compound, and ionic compounds or ionic bonds are one of the strongest intermolecular forces, and so we can say that this is basically our answer. Okay, so they have, okay, so this is, I guess this is supposed to be methane, so we can say here that this is supposed to be CH4, and it's supposed to be CH3, OCH3, H3OH, and CaCO3. Okay, so this is the answer from increasing boiling point. So we can say increasing okay. So I can say that this is correct. And so basically that was the end of our session. If you really like this Q&A, please subscribe to OneClass, share, comment, share, comment this video, and look at our other videos. And if anyone has any personal questions, you can look at the description box below and follow the links and ask your own questions. Other than that, I'm Shanjida. Today we went over some commonly asked chemistry questions, both at the high school and university/college levels. Other than that, I'll see you soon.